Thank you, and thank you to the Stavros Niarchos Foundation for inviting me and hosting me here. It's quite a daunting challenge that I see that the conference members have been discussing and challenging themselves with. When I arrived in New York, I saw a bus go by, and on the side of the bus, it was advertising a new HBO comedy. And the HBO comedy was called Silicon Valley. Everyone wants to be an icon. But it's important because it's very demonstrative of, how ingrained entrepreneurship, and especially high-tech entrepreneurship, is in the American society and culture. And I think that's one of the things that makes the country such a great success that it's been. But sometimes to understand how that happened, we have to go back in history, and we have to find those seminal moments that really put the country on a path to build and take advantage of the technological growth that came from the scientific discoveries that occurred in the last century. Now, in trying to figure out what I could say to this conference, I found a document, the document that I've read many, many times, and I've found very inspiring and very instructive in how I decided to take on some challenges in my country, in Canada. But it's something that, I encourage all of you to read. It's on the web, and as I go through the first 4 slides, the address, the URL, is at the bottom right corner. So if you could just jot it down. I'm going to go through it fairly quickly, and I'm going to try and put it in context for you. But it's a small document. It's like 70 pages, and it's got a really good 15-page summary at the beginning. But as a historical document, it's a seminal piece of work. And it begins as a correspondence exchange between President Roosevelt and Vannevar Bush, the director of the Science and Research group. Now, before I get to it, I want to just give you a sense of let's put it in context. Roosevelt writes a letter to Vannevar Bush in 1944. In fact, it's November 17th, 1944. It's during the World War. It's nearing the end of the World War. And what's important for you to sort of put yourself in that state of mind is realize that this administration and this president have seen the enormous success and power that they brought to bear by bringing scientists, theoretical physicists, chemists, medical doctors, engineers together to help them turn this war around and win it. Now keep in mind that all this is happening in secret. So the public doesn't even know. This is not even a voting issue, right? So this is a government and its administration that has been enlightened and has seen something very powerful and very special, and possibly for the first time. And so with that, we'll go to the first slide. This is the letter, and if you go to that website that's at the bottom, I don't know if you can read it with the blue, but I'll be happy to get it for you later. This is President Roosevelt's letter to Vannevar Bush, director of the Office of Scientific Research and Development during World War II. Vannevar Bush was assigned a very large, critical task of marshaling the resources in the United States, interacting with other governments, allied governments, and bringing to bear all the scientific and research and engineering resources of the country to win the war. So this is November 17th, 1944. And I'm going to read you a quote from that letter. And again, if you read the very first part of that letter, it says, this experiment. So Roosevelt sees what Vannevar Bush is doing, marshaling all the resources, scientific and engineering resources of the country, as an experiment. In other words, it hasn't been done before, at least in his exposure and understanding. He says, "There is, however, no reason why the lessons to be found in this experiment cannot be profitably employed in times of peace." So obviously, President Roosevelt feels that the war is coming to an end, right? And his administration and himself have seen firsthand the power of putting all those resources together and giving them virtually unlimited financial and engineering and resources to fulfill their mission. There is, however, no reason why the lessons to be found in this experiment cannot be profitably employed in times of peace. The information, the techniques, and the research experience developed by the Office of Scientific Research and Development and by the thousands of scientists in the universities and in private industry should be used in the days of peace ahead for the improvement of the national health, the creation of new enterprises bringing new jobs, and the betterment of the national standard of living. So this is political will at its greatest in this line of endeavor. So they've seen it firsthand. This isn't even a public vote issue because the public has not seen any of this. And if you read this letter, he starts off by saying, you know, all this great work that you and your team have done, and all these scientists, no one knows and may never know. Although I'm hoping that after the war, we can let people know the great work that you've done. So this is a perfect example of pure political will that has been enlightened by an understanding of the power of basic research and industry. And so these are a couple of the questions that he asked. He asked 4 questions, but these are the 2 I'm going to talk about today. What can the government do now and in the future to aid research activities by public and private organizations? The proper roles of public and private research and their interrelations should be carefully considered. Now he's talking about innovation in public policy in that sentence, in that question. Saying, how can we innovate further with what we just learned? Can an effective program be proposed for discovering and developing scientific talent in American youth, so that the continuing future of scientific research in this country may be assured on a level comparable to what has been done during the war? So he's talking about his youth. He's talking about, we know the end of the war is coming. We know we're going to have some peace. We've seen the power of basic research given unlimited funds. And we've seen the power of our youth and scientists that have been given the task of helping us win this war. So it's an ambitious vision. And he writes this letter to Vannevar Bush, November 17th, 1944. Now, Vannevar Bush takes 8 months to respond to this letter. Okay? So he responds in July 25th, 1945. So if we go to the next slide, you can see the response of his letter, or his letter response. July 25th, 1945. Why did it take him 8 months to respond? Now he says in his letter that I had to meet with all my committees, and we had to come up with answers to your question, and we had to do all these things, and he says later in his letter, but actually what I'm going to tell you is my idea. But I'm going to include all that committee work as an addendum to my report. But this is my idea. And what's interesting is he waited until the successful test at Trinity, the first atomic bomb in New Mexico. So the first atomic bomb was detonated successfully in July 16th, 1945, 10 days before he sends his letter to President Roosevelt, replying to his request. So it's kind of interesting if you look at, the political positioning of this. He wants to make sure that he's on a firm footing when he proposes his idea, because it worked. Because the last thing he'd want to do is tell him what we should be doing, and it doesn't work, right? So it's just interesting to watch how these things develop. But what's important is that he took the opportunity to really define and really connect and describe the first time the qualitative and quantitative connection between basic research and jobs and prosperity. That's what this document's all about. The document's called Science, the Endless Frontier. And it's a seminal work. It really lays down the policy that the United States had actually implemented after this. And I believe is one of the main reasons why the United States was so successful from an industrial point of view. Now what's interesting is, and I'm gonna there's two parts of this report I'm gonna focus on shortly, but I wanted to read you the last line, which kind of gives you what's important is the enthusiasm in this line. Because many of these problems that countries have, and you know, and sections of the population have, it's from a lack of confidence, right? So enthusiasm's important, passion's important. He ends his letter by saying the pioneer spirit is still vigorous within this nation. Science offers a largely unexplored hinterland for the pioneer who has the tools for his task. The rewards of such exploration, both for the nation and the individual, are great. Scientific progress is one essential key to our security as a nation, to our better health, to more jobs, to a higher standard of living, and to our cultural success and progress. So here is two sections that he puts a great deal of emphasis in his report to President Roosevelt. Now, what's interesting about what he says is that if you read this, and I'll read this to you in a second, this could have been written today. These are issues of the day. I'll read it to you. It says, scientific progress is essential. The most important ways in which the government can promote industrial research are to increase the flow of new scientific knowledge through support of basic research and to aid in the development of scientific talent. That's the best role for a government to play into promoting industrial research, is by supporting basic research and educating youth in scientific talent. In addition, now this is where it could have been written today. In addition, the government should provide suitable incentives to industry to conduct research, because that's how it gets commercialized. That's how it gets translated to value. We need to do basic research, but it gets translated by industry. So we need to provide those incentives. And he has two areas that he focuses on. By clarification of present uncertainties in the Internal Revenue Code in regard to the deductibility of research and development expenditures as current charges against net income. Research tax credits, research industrial grants, right? Basically, he's talking about the tax code. This is 1945, in the middle of the war. B, by strengthening the patent system so as to eliminate uncertainties which now bear heavily on small industries, and so as to prevent abuses which reflect discredit upon a basically sound system. This could have been written last year. In addition, ways should be found to cause the benefits of basic research to reach industries which do not now utilize new scientific knowledge. This is about modernizing industry, any industry, not just high tech. And again, July 1945. And then he says the other one, the other part of his two-part proposal. We must renew our scientific talent. And there's a few things that he says here that are very, very important. The responsibility for the creation of new scientific knowledge, and for the most part, its application, rests on that small body of men and women, who understand the fundamental laws of nature and are skilled in the techniques of scientific research. So you don't have to get everyone in the country doing scientific research. You just got to really focus and support a small number. We shall have rapid or slow advance on any scientific frontier depending on the number of highly qualified and trained scientists exploring it. He goes further, the training of a scientist is a long and expensive process. I mean, we all know this. To get your PhD and postdoc in physics, you're in school for 30 years plus, right? So if we decided to make a change today, we're not going to see anything for 30 years. So this is a long-term plan. The training of a scientist is a long and expensive process. Studies clearly show that there are talented individuals in every part of the population. This is really important. So he's saying, you know what? We don't have to wait 30 years. They already exist. We have to identify them. They're there. We know they are. And we don't need a lot of them, but we know they're there. And we can build success on a very small number. So it says, studies clearly show that there are talented individuals in every part of the population, but with few exceptions, those without the means of buying higher education go without it. So that's also important. So even though that number is small, the number I have access to a higher education, in his opinion at the time, is even smaller because it's the intersection of the two. If ability and not the circumstance of family fortune determines who shall receive higher education in science, then we shall be assured of constantly improving quality at every level of scientific activity. The government should provide a reasonable number of undergraduate scholarships and graduate fellowships in order to develop scientific talent in American youth. So the two things that he really focuses on, he proposes the National Science Foundation, a national single-body granting foundation to support graduate studies and research across the country. He proposes increasing it many-fold and proposing that it's going to be kept up for a decade in the minimum. And then the other thing he talks about is identifying and providing scholarships to those undergraduates with the most aptitude, that show the most aptitude, and finding them and really helping them along. So what's important here is the certainty, the confidence he had that these are the things that needed to be done to really set the success path for the country. This is, again, 1945. So if we look at what happened, so this is a snapshot of the last century and a little bit of this century. But if we look at what happened, it's important to get a sense of that history and what were these seminal moments. What we've just talked about is just before the invention of the transistor, 1945. 1944, 1945, the ending of the war, the atomic age, the semiconductor revolution. What's interesting is that 40 years earlier, we finally discovered something that was postulated by early Greeks. This idea that all matter is made up of atoms, these small particles. And at the time, they were thought of being indivisible particles. But what we sometimes forget is that we had no experimental proof of an atom until 1905. And all at once we knew that the atoms existed, and it was actually one of Einstein's papers that explained Brownian motion, and he showed what it was by showing that statistically it was atoms moving these oil particles around. At the same time, Einstein described the photoelectric effect, which was a big problem decades leading up to 1905, where he basically said, there's these atoms and they behave in a quantized way. And you know what? Energy can be, the energy problem that we have, it was called the ultraviolet catastrophe, could also be explained using this idea of a quanta. So we have the birth of quantum mechanics, which is the most successful theory in the history of science, especially physics. It has been accurate to the highest number of decimals that we could test it. And so with that basic understanding, we started thinking about these things that we can't see. We had a tool that allowed us to not only predict it, but control it. That led to a lot of things. But the biggest change was this idea that matter was quantized, It allowed us, another thing that he did, it's amazing how many papers he wrote in 1905. The other thing is, of course, he showed us the equivalency of energy and matter, derives E equals mc squared. That's what drives the Manhattan Project, gives us the atomic bomb, and that brings us to where we are today in this in history on this Vannevar Bush report. Now, the important thing is that Roosevelt and his administration had the insight and the good understanding to say we need to keep this up, even when it's over and we all party and relax and feel successful. He said, no, we got to keep this up because the scientists are telling me that this is just the beginning. There's amazing stuff we can do with this newfound understanding of reality. And so in 1947, actually December 24th, 1947, Bell Labs, which is probably one of the more successful industrial basic research labs. It's hard to do today. Back then, of course, they were mandated to do it in order to keep their monopoly for local and long-distance telephone service. But they invent the transistor. There is no way that you could invent a transistor if you didn't understand quantum mechanics. There's no way. It's not natural. It goes against everything you could see from a common sense point of view. So in 1947, December, they invent the transistor. In New Jersey, not Silicon Valley. It was invented in New Jersey. And then those people left, those researchers left, and they went to California. And they started businesses. Fairchild, Shockley Semiconductor, Intel. And that just grew. And what happened was, and Gordon Moore, one of the founders of Intel, discovered an interesting trend, is that with modern lithography techniques that we're using to make these integrated circuits, the equipment allowed us to make the geometries that we're exposing on silicon smaller every 2 years. And we've been able to ride that wave for the last, for 70 years or more. Now, that gets into where I went to school. I built a computer in my basement. It was one of the first microprocessor chips that came out. PCs weren't even invented yet. Interesting, years later, I had a chance to meet with Steve Wozniak, and we both realized that we had invented the same video circuit for the computer at the same time. I put it into a product that I started selling in display systems for industry. He put it into a computer and invented the computer. I stuck with that system and eventually came up with the first smartphone. But I discovered, and my colleagues discovered, that the incredible power of technological growth and basic research that drove it. And in fact, we decided, we came up with an idea. It's a simple way of thinking about it. We came up, and this was our passion, was that today's theoretical physics is tomorrow's technology. Because that's exactly what happened back before. So when you looked at, does it go backwards? Yeah, there. So if you look at that, theoretical physics, this is stuff of the mind. A lot of what Einstein did wasn't in a lab. He did it all in his head. That theoretical physics, 40 years later, became the technology that ended the war. 47 years later, it became the beginning of the information age. So we realize that today's theoretical physics is tomorrow's technology. But the other thing is, now for a second, we have to step back and say, well, I'm from Canada. I wasn't in the United States. I could just look with envy at what was happening in Silicon Valley and the explosion of value creation, jobs, wealth, cultural shift, confidence, and security that the information age in Silicon Valley brought to the United States. And so when I looked at what was happening in Waterloo, Canada, what I realized was what we had done on our singular mission to really build mobile data is that it was unique in our country. It was surprising because I lived through my whole life thinking technology, everyone did technology. It was cool. It was amazing. We were right in the thick of things. And what I didn't realize, we were in the end of it. We had just joined in this global Silicon Revolution. We joined into it at the end. If you look at Canada, it's sad, but we really only got into it as it was commoditizing, as we were nearing the end of Moore's Law. And what I realized was that we literally, as a country, sat out the first Silicon Revolution, or sorry, the first quantum revolution that we all call the Silicon Revolution. And so my partners and I, we basically decided that we're going to do what we could to make sure that Canada was prepared for the next revolution. And because we shared a joint passion for theoretical physics, and because we understood that today's theoretical physics is tomorrow's technology, we decided that we could get Canada focused on theoretical physics. Now, it was much harder than it looked, but what's amazing to me is what the leadership focus and vision of a small group of motivated people can accomplish if they pursue it with focus, discipline, and perseverance. It takes time to do this. And we were fortunate. We started Perimeter Institute for Theoretical Physics in 1999 with 4 researchers that we were able to recruit. And we went with a large philanthropic gifts that were eventually matched by government. And then 2 years later, based on what we found out from the researchers that we were hiring, we decided to start the Institute for Quantum Computing as an experimental facility, sister facility to Perimeter theoretical physics capability. And so in those 2 years, we saw the birth of a pure theoretical physics institute in Waterloo, Canada, and the Institute for Quantum Computing at the University of Waterloo, which is a strong engineering, computer science, math co-op school. Now, we stayed with it. A lot of investment, a lot of, at this time, now this is the difference. If you remember, Vannevar Bush and Roosevelt, that was purely political will. When we started Perimeter and IQC, it was philanthropic and industrial will. Right? That was entrepreneurs getting together and saying, let's do something together. This is something that's important to us, it's important to the country, and it could be important to the world. And so we got together, and this was an example of philanthropic and entrepreneurial will. And we were fortunate enough to be able to get our message across to government and to citizens so that we could get the political will aligned with us. And they supported us with matching grants and other support. So that this actually started to thrive. And Canada went from really very little theoretical physics to, possibly, well, we know it's the largest theoretical physics institute in the world, but last year Stephen Hawking basically said when he was here helping us launch the new Quantum Nanocenter at the University of Waterloo, he said that Perimeter Institute is now one of the world's leading centers in theoretical physics, if not the leading center. Now, this is not bragging. What this is showing you that Canada, which is 1/10 the size of the United States, didn't ride out the Silicon Age at all. In fact, if you look at the number of companies that really were high-tech drivers, you're talking about maybe less than 2 dozen. The other parallel to draw is that the province of Ontario, which is where we are, is about the same size, population-wise, as Greece. And so, there are a lot of parallels, but the real takeaway is that it requires this leadership, focus, and vision of a small group of motivated individuals. And if you can leverage that within that small body of men and women that have the aptitude, and interest in scientific research, you can create, something that has tremendous value in a very short period of time when you start thinking about the kind of scale of these kinds of endeavors that we've seen historically. And then the sister institute, Institute of Quantum Computing, Dave Weingard, the 2012 Nobel laureate in physics, was there, and he said, as far as I can tell, IQC is the single largest center in the world for quantum information science. But again, why is that? Because we focused. We targeted quantum information science and quantum computing, and we're now one of 5 centers in the world. If you were to look at, there was a study that was put out by the Max Planck Institute, mapping scientific excellence, and they put Perimeter Institute in the top 5 in the world. And that includes 3 experimental research facilities and universities. So if you took out just the theoretical physics institutes, we were second to Institute for Advanced Study in the US. So very successful, very high impact to our province and our country. So, how is that relevant to what we're talking about? I love this painting. I think it's incredibly relevant. And again, you have to look at it from a contextual and historical viewpoint. So this is a painting called The School of Athens by Raphael, 16th century. What's important is this is how the world viewed Athens. Right? This is how they viewed the history of Athens, the School of Athens. And it's an amazing picture because it's got all the great historical Greek figures. And to think that democracy was born in this culture at that time. And to think that these individuals that came out were able to invent modern philosophy, mathematics, science, physics. In fact, Anaximander, who's the person, if you look to the left bottom, there's someone looking over the shoulder, and it looks like he's copying from him, doing, cheating on his homework, but he's not. And the painting is trying to get across that he's taking theory and he's looking at the world and saying, how can I apply this to the world? How can I test this theory, this philosophy to the world? And that's basically science, right? How we test our theory against nature, and that gives us an understanding of and control over nature. But again, if you think about the history that Greece has, and it shouldn't surprise us if they decided to invest in education. It shouldn't surprise us if they decided to invest in basic research and industrial research. It shouldn't surprise us. But what I found is it really does take leadership, and it does take vision, and it does take real intense focus by those people that have the will to do it. And it's going to require, of course, political will, but today, at times of peace, it takes philanthropic and entrepreneurship will to really get this kind of vision started and put in place and provide enough excellence to have that kind of impact over a sustained period of time. But what I can leave you with is this. It worked in Ontario, Canada, in 15 years. It could work anywhere. Thank you.
Dr. Lazaridis will take a few questions now. If you would like to raise your hands so we can see you. Yes, please, the lady in the back.
Hello, my name is Stella Kunilaki and I'm a postdoc at MIT. Thank you very much for your talk. I wanted to ask you, you talked about the need to create a pipeline of scientists, starting from elementary school to college. But yet also, Greece is a country that's facing urgent financial circumstances and perhaps need for immediate results. My question is, if you had $100 today, where would you put them? In the case of Greece, would you invest, how much of these $100 would you put in K through 12 STEM education? How much in higher education and research? And how much in VC money for entrepreneurship right now? Thank you.
All of it. That's a very good question. I mean, if we had only, I mean, these are tough things to answer, and we can't take them too flippantly. I mean, these are important questions. You know, if we only had a small amount of money, how would we divide it up? What you said was important, though. You said STEM education, and that's the key. Look, we need all the rest of like all education is important. It's important for a well-balanced individual. But if our goal is to get ready for and be a part of the next technological revolution, the next scientific revolution, and really technological society and economy of the future, we really need to heavy set and invest in STEM education. So, you know, it's sciences, mathematics, engineering, technology. So that's really important. So I would say, you know, it's important to teach the importance of it, because, especially in younger grades, because what happens, I've found, is that there's a tremendous interest by most children. And you'd be surprised, there's actually a larger number of young women, young girls at that point, who really are fascinated and intrigued by science and math and basically STEM subjects. Something happens in our culture as they get older, and they're not as encouraged to stay with it. And so what the takeaway from this, and you know, Vannevar Bush realized it, and I think we realize it today, is that what's important is to identify those individuals, whether it's public school, whether it's high school, university or college or grad, that show an aptitude and interest, and then make sure that we encourage the hell out of them. You know, just encourage them. Take away barriers. You know, don't make it, you know, don't make it a decision for the family that has to basically mortgage everything to put their kids through university. Because if the economy is so bad that it's hard for us to see past the immediate issues and challenges that we have to the long-term sustainable strategies that have worked for, you know, the last century, it's even harder for them to make that decision to support their children going to school. And that's even if it's a free education, because they still have to, you know, they still have to find a place to live. They have to feed themselves. They have to get around. They have to buy their textbooks and their computers. And if they can't even get a job, you can imagine how difficult that would be. But the important takeaway from all this is that if we could identify them, we don't have to wait 30 years, because they're in the pipeline already. So we need to support them. And then we need to make sure that we get an over supply, if we can, from historical numbers of those people that are getting themselves trained and excited about a technological future, because, you know, more and more of the economy is going towards high technology.
Good morning. Thank you very much. Bob Goodman from Rutgers. So I love the Vannevar Bush story, but the other story, this is just sort of a comment. The other story that I love is the story coming out of the Civil War, Abraham Lincoln signing the Morrill Act, which created the land grant for states to create colleges to teach agriculture and the mechanic arts. And out of that has grown the enormously successful public research university system in the US. Both of these are examples, though, in today's world, and this is my point, where it seems like the social contract is kind of wearing out. The public investment in these institutions, in the NSF, in the land grant system, are declining. And I am just thinking forward to the notion that there are lessons here for our topic today, Greece and its future. How do you, or would you, try to build in ahead of time in the planning mechanisms that would maintain the public commitment to what we're talking about, education, STEM education, and so forth?
Yeah, so that's a great question. It's a great observation that the political will, and this is one of the things I was trying to bring out in the talk this morning. This idea of political will and philanthropic and entrepreneurship, private will, and it's great when it all lines up. It's the best thing that could ever happen is when you line all three of those together and they're working together on a common purpose, because you're bringing the most to bear on the opportunity. Historically, what you're saying is that historically, those things that had the most public will and produced the greatest results in our history, maybe that public will is not as strong today as it was then. So I agree with that. And I think that's where the power, the opportunity, and the responsibility of today's foundations and charities and philanthropic groups and individuals is necessary. Because sometimes it's important for them to try and lead the way when the public will is so mired in real issues, immediate concerns, immediate problems. Sometimes, they need to be encouraged that there is a path that works. It requires a different approach, and in many cases, it may require time. But historically, it has always succeeded as a strategy.
Well, thank you for this inspiring, I would say, lecture. I use the same picture, the Scuola di Atene, in my Coralia attitude, but I will tell you something. In the front, if you go from abstract physics, which is Parmenides, Anaximandros, Anaximenes,
yes.
What I use is the idea they succeeded because they used the agora principle, which is clustering. They were coming together and discussing items which we don't do anymore, unfortunately. Now, the next step is Pythagoras. So from basic science to abstract mathematics, and then you go to Euclid, which is Euclidean geometry. And next door is Archimedes, which is engineering. Now, what I used to say to the kids is, with Euclidean geometry, you can change Greece by using three-dimensional vision, which is in that box here, Euclidean geometry, to set up the new way of looking to ancient Greece. And I call it anti-Hollywood aspect, because the Hollywood way of showing ancient Greece is absurd, but very popular. You can create a new way of reconstructing ancient Greece with this picture on the way I told you. So,
well, I think, and I agree with you, I think the important thing with that picture is in that, there's two or three parts that are important that we haven't talked about. One is they have a light. We talk about in consumer electronics and in innovation circles, entrepreneurship. We talk about a license to innovate. So the public needs to give you a license to innovate. And if you lose that license, it's really hard to promote your brand, right? So Greece has a license to innovate, right, because of their history. Canada, we're only 200 years old. Like, we don't even, we have no history, let alone science history or mathematics history. But you know what? It didn't stop us from being successful, right? And so the beauty of Greece is already starting a leg up because it has the license to innovate. It has that history. What's also interesting about the picture, and you mentioned, well, you talked about at the right-hand corner, you've got Euclid using his compass. Did you notice how many women, young women, are working with him, studying with him? See, that was another important thing in that painting, because the world recognized that Greece was more inclusive at that time. That's right, she's there. Yep. All right. Well, I think that's it, right? We're way over time. Thank you.
Thank you again, Dr. Lazaridis. So it's time to move to our first plenary session on addressing youth unemployment. What works, what fails. My colleague Stelios Vasilakis will be moderating the next panel discussion and introducing the speakers and panelists.